Hello viewers, welcome back to the course on matrix computation and its application. So, this is a lecture number 27. In the previous lecture we have started with the one example. So, today we are going to start with that example. So, in the last lecture we have started with the example that suppose we have a set of polynomials of degree less than equal to 3, and this is a vector space I know and of dimension 4. So, from there I choose two subspaces. One subspace is U with all the polynomials such that P1 is equal to 0. It means that 1 is the root of this polynomial, and W is another subspace of V in which the P dash means the derivative of the polynomial and taking the value at x equal to 1 is 0. Then we want to check that what will be about U plus W, U intersection W, U and W in terms of dimensions, bases and the extension of each of these bases to the basis of V. So, this thing we need to do for this one. Now, we know that it is the vector space set of polynomial of degree less than equal to 3. This is of dimension 4, and this can be written as a polynomial a plus bx plus cx square plus dx cube, where a, b, c, d are belongs to the real number. So, we are talking about the real polynomial, and the standard basis for this is 1x x square x cube. So, this thing is there. Now, so from here, now I take the set U. So, U is all the polynomials belongs to the vector space V such that P of 1 is equal to 0. It means that I am taking U as the polynomial. So, polynomial we have started with a plus b. So, I will take a plus bx plus cx square plus dx cube such that, so if I choose P1, so this is my P such that a plus b plus c plus d is equal to 0, because P1 will be a plus b plus c plus d, and this value is given to me, that is 0. So, this is the set which contain all the polynomial of such type. Now, from this condition I can, because this is a 4 variables and with only one condition, so I can write my a as minus of b plus c plus d. And from here I can write that my U will be, so instead of a I can put minus of b plus c plus d plus bx plus cx square plus dx cube. So, all these set of polynomials where b, c, d belongs to the real line, and from here if you see, then I can have from here. Now, what I can do is I can take the b common. Suppose I take the b common, then I will get x minus 1 plus, then I take the c common. So, c can be written as x square minus 1 and d will be x cube minus 1. So, this is a set of polynomials. Now, from here you can see that this set of polynomials contains only 3 coefficients to be found out, that is b, c and d. So, now that is my U. So, from here I can say that my U is spanned by, so I can say that U is spanned by the set of polynomials. So, that is the polynomial is x minus 1, x square minus 1 and x cube minus 1, because they are spanning the whole U. Now, so this is a spanning set. Now, also, so suppose I take this set as maybe I can call it B1. So, also the set B1 is linearly independent. How we can say that this is linearly independent? So, because I just take the linear combination. So, suppose I take the linear combination alpha x minus 1 plus beta x square minus 1 plus gamma x cube minus 1 is equal to 0. So, this is the linear combination I have taken, and from here I can write the corresponding equation gamma x cube plus beta x square plus alpha x minus alpha plus beta plus gamma equal to 0. So, this is true for all x. So, if it is true for all x, it means we have to compare the coefficient of same each terms on both sides, and right hand side is the 0 polynomial. So, this is basically a 0 polynomial, and I am taking this true for all x. So, which implies that in this case my gamma will be 0, my beta will be 0 and alpha will be 0, because constant term 0 and the coefficient of x cube, x square, x all are becoming 0, and from here we can say that the set or the polynomials x minus 1, x square minus 1, x cube minus 1, this set is linearly independent. So, now if it is linearly independent, from here I can say that the set B x minus 1, x square minus 1, x cube minus 1 is a basis for subspace U. Now, one thing is very much clear to us, that U is a subspace, because in this case I have not proved this one, that if whether U is a subspace or not, but it is U is a subspace, because I can take from here, because two conditions we need to satisfied. So, I can take the polynomials P1x plus P2x. Then from here I know that if I write P1 plus P2x, and this will give me, it will satisfy the condition that P1 plus P2 at 1, that will become P1 1 plus P2 1, and both are 0 plus 0. So, that will be 0, and similarly the scalar multiplication. So, it is a subspace and its dimension. So, dimension of U is 3. Now, we know that U is a subspace of vector space V, and also I know that the dimension of V is 4. So, what I can do is that I can extend this basis of U to the basis of V by the extension theorem. So, by using extension theorem, we can extend the basis B. So, this is the basis B, I have taken B1 basically. So, I just write it B1. So, we know that, so by using this extension theorem we can extend the basis B1 to the to a basis, not the to a basis for V, because for V the standard basis already we know, but this can also be extended. Now, from here I can write that since the, so what I can write is that 1, if you see from here, 1 does not belongs to the spanning set of x minus 1 x cube minus 1, because anything constant multiple cannot delete or cannot cancel out the x cube, x square or x. So, it means that 1 cannot be written as a linear combination of this one. So, these things you can verify by the same way that I write alpha x minus 1 plus beta x square minus 1 plus gamma x cube minus 1, suppose it is equal to 1. Then from here I will get that gamma x cube plus beta x square plus alpha x minus alpha plus beta plus gamma is equal to 1. And suppose this is true for all x, now from here you can see from here that if I take this one, then from here I can write that my alpha plus beta plus gamma will be minus 1 and alpha is equal to 0, beta is equal to 0, gamma equal to 0. And this is not possible, that if alpha, beta, gammas are zeros, then their summation will be minus 1. It means that from here I can say that this system is inconsistent. So, above, so this is my, basically it will become a system of equation. So, the above star is not possible. So, from here, which implies that 1 cannot be written as a linear combination of this. So, from here I write the basis B as 1 x minus 1 x square minus 1 x cube minus 1. So, it is, so this set is Li, and of course, it is having the 4 vectors. So, from here I can say that B is a basis for the vector space V, and dimension in this case of V will be 4, and that is already we know that the dimension is equal to 4. Okay, so, from here you can check that this is true. So, after doing this one, the same way I will go for the subspace V. Now, I will discuss about the W subspace. So, W is a subset which contain the polynomial Px belongs to V, that the set of polynomial, such that P dash x, P dash at x equal to 1 is 0. So, now of course is a subset of the vector space V. Also W is a subspace of V. How it is a subspace of V? Because let I take P1x and P2x belongs to W, then P1 plus P2x, this one I want to see. So, it is a two polynomials P1 plus P2. So, basically this is equal to P1x plus P2x. Now, what about P1 plus P2 1? So, that will be equal to P1 1 plus P2 1, and this is 0 plus 0, that will be 0, because these two polynomials are belonging to the W, and in the W, okay, so I should take the derivative. So, let us, no problem, we will take the derivative. So, derivative also we know this one, and we also know that this is equal to this. So, this is P1 0 and 0, so that will be 0. It means that sum of two polynomials is also belongs to the set W, and also alpha p x, this one I want to do. So, I just want to take the, so this one I want to check. So, I just take alpha p derivative. So, this one I will know this will be equal to p dash x, and this value alpha p dash at 1, this will be equal to alpha p dash at 1, and this is alpha into 0, that will be 0. So, it means that the scalar multiple is also belongs to the set W, and vector addition is also belongs to the W. So, it means that W is a subspace of V. So, from here I can write my W as, so this is a set of polynomial a plus bx plus cx square plus dx cube, such that if I take the derivative of this one, so then it will be b plus 2c plus 3d is equal to 0, because the derivative of this one will be b plus 3 c x square plus, not c, b plus 2 c x plus 3 d x square. So, this is the derivative of the polynomial, and if I put 1 here, so it will become b plus 2 c plus 3 d, and this should be equal to 0. Now, from here, now the same way we can do. So, these conditions is to be satisfied. Now, from here I can take my b as minus 2c minus 3d, and now based on this one, so I can write my set as A. Instead of b, I can put minus 2c minus 3d x plus c x square plus dx cube, and this will become A plus, so I just take the common c, so c will x square minus 2, and then I will take the common d, so it will be x cube minus 3, so this one. Okay. So, x will be there, no problem, this x will be there, because I am taking with respect to x. So, x square minus 2x, x cube minus 3x. Now, from here you can say that the W is spanned by the set, so I call it B2, spanned by the set. So, here I can have 1, x square minus 2x, x cube minus 3x. So, this set is there. So, it is spanning the whole W. Also the set B2 is linearly independent. So, this one is linearly independent because it is a constant term, it is a x square, x cube. So, different order of the polynomial. So, definitely these are the linearly independent, and from here we can say that W. So, I can say from here that B2 is a basis for subspace. So, it is a basis for the subspace W, and which implies that the dimension of W will be 3. So, it is of dimension 3. Now, again the same way, that since W is a subspace of V, so we can extend B2 to a basis for vector space V. So, what we can do that? We can extend this one, and from there, so since now if you see from here that this contain the second degree polynomial, third degree polynomial and the constant term. So, x is not there. So, I from here that x does not belongs to the span of 1 x square minus 2x and x cube minus 3x. X cube minus 3x. So, it is does not belong to this span, this one. So, from here we can say that this set 1 x, x square minus 2x and x cube minus 3x is a basis for V, and now it is a 4 dimension. So, by extension theorem we are able to extend the basis to the basis of V. So, this thing is over. Now, we go for the next subspace, and that subspace is what about U intersection W, because this one is already we need to find out what will be U intersection and U plus W. So, these things we have to find out. Now, the space we from the previous knowledge we know that U intersection W is also a subspace of V, because it is an intersection. And now, from here I can find that U intersection W will contain all the polynomial p x belongs to V such that p at 1 will be 0, p dash at 1 will be 0. So, it contains all the polynomials which belongs to the set U. So, if it is a p 1 which belongs to the set W, which is a p dash 1 equal to 0. So, from here I can write that this can be written as the set of polynomials, that is a plus bx plus cx square plus dx cube, such that a plus b plus c plus d equal to 0 and b plus 2c plus 3d equal to 0. So, this is the set we are going to have. And now, from here, from these two conditions, we can find out from here. See, from here I know that from here I can write b will be equal to minus 2c minus 3d, and from the first one I can write, because in the b I can write here. So, I can write everything a can be written as minus b minus c minus d, and which can be written as minus. So, b I can put here. So, it will be minus 2c minus 3d minus c minus d. So, from here I can write from here that this will be equal to, so it is minus, so 2c minus c, so c, and this is minus plus 3d minus d, so minus 2d, that will is my a. So, a I have written in the terms of c and d, and b we have written in the terms of minus 2c minus 3d. So, these two constants can be written in terms of c and d, and now from here you can check that this polynomial becomes now I can write, instead of a I can write c plus 2d plus b is minus 2c minus 3d x, and then I can write plus cx square plus dx cube, and from here I can collect the terms. So, now from here I will collect the terms corresponding to c. So, it is x square minus 2x plus 1, and d is x cube minus 3x plus 2. So, it is x cube minus 3x plus 2 and x square minus 2x plus 1. So, this is all the set of polynomials. Now, from here, which implies that u intersection w is spanned by the set, I call it B3. So, this is x square minus 2x plus 1, and another is x cube minus 3x plus 2. So, this is a polynomials we got from here. Okay. Yeah. Now, also B3 is linearly independent because it is a third degree polynomial, it is a second degree polynomial. So, the B3 is linearly independent. From here I can say that B3 is a basis for u intersection w, and from here I can say that the dimension of u intersection w is 2. So, now I have able to find the dimensions, and that is equal to 2. So, from here you can say that this is of dimension 2. Now, since u intersection w is also a subspace of vector space V, so we can extend the basis B3 to a basis of V. So, it is of dimension 2. Now, I can extend this to the to the basis of V. So, that we can do the same way we have done. So, this is very easily we can do. We can induct 1 from there, that because 1 is not there, and x we can include, and from there you will see that this will extend it to the basis this way, because you can say from here that, so I can 1, because 1 does not belongs to the span of x square minus 2x plus 1 x cube minus 3x plus 2. Also, x does not belongs to the span of x square minus 2x plus 1 x cube minus 3x plus 2. So, from here I can extend the set as 1 x square minus 2x plus 1 x cube minus 3x plus 2. So, now I can, that is a basis of V. So, from here you can check that we are able to find 3 type of bases, different bases for the V. First we have found this one, then we have found the another set, this one, and now we are able to find this set. So, it is also a basis of V using the extension theorem. Now, based on this one, now I am going to do the find out the another subspace, that is we call it u plus w. Then how we can find out u plus w? So, in this case, so this is the last one I need to do. So, u plus w, basically u plus w is contained of the polynomials px plus qx, set of all the polynomials such that px belongs to u and qx belongs to w. So, this is a set of polynomials, because I know that u plus w, that is also a subspace of the vector space V, and it is made up of the polynomial vectors coming from u plus the vector coming from the w. So, this is set of the polynomials we are going to take, that px is coming from u and qx is coming from w. Now, from here, based on this one, we can say that so u plus v or u plus w is basically a set of polynomials. So, I can write the set of polynomials. So, the px, if I take, so I am taking the px, so px should be belongs to u, and if it is belongs to u, then I know that its bases are this one. So, these are the bases of u, yeah, x square, x minus 1, x square minus 1 and x cube minus 1. So, I can write down that. So, it containing coming from this one. So, I can write that, suppose alpha 1 is x minus 1 plus alpha 2 x square minus 1 plus alpha cube, and alpha cube is coming x cube minus 1. So, this is the polynomial coming from w from u plus, now it is coming from the w. So, in the w I know that the basis of w is 1 x square. So, this is the basis for w. So, 1 x square minus 2 x, x cube minus 3 x. So, it is 1. So, I can call it beta 1 into 1 plus beta 2, that is x square minus 2x. So, x square minus 2x plus beta 3 x cube minus 3x. So, this is the polynomial we are going to have, such that alpha 1, alpha 2, alpha 3, beta 1, beta 2 and beta 3, that belongs to the real number. So, this is the set of polynomials that is coming in u plus w, and also, so u plus w we are able to write. Now, we need to find the dimension of u plus w. So, I can say that u plus w we already know that is spanned by the set of polynomials. So, I am taking all the vectors belongs to the spanning of u and spanning of w. So, it will be x minus 1, x square minus 1, x cube minus 1, 1, x square minus 2x and x cube minus 3x. So, this is the basis, I call it B4. So, this is a set that is spanning u plus w, and but it contains the 6th element. Now, from here I can write that the since u plus w is also a subspace of V. So, which implies we already know that the dimension of u plus w is less than equal to the dimension of V, that is equal to 4. It means its dimensions at max can be 4. Now, from here also, using the theorem, we know that the dimension of u plus w is equal to the dimension of u plus dimension of V minus dimension of u intersection w. So, from here I know the dimension of u was 3, dimension of v was w was 3 minus the dimension of u intersection w is 2, because it is 2. So, from here it is 6 minus 2, that is 4. So, if the dimension of u plus w is 4, so now since dimension of u plus w is 4, that is equal to the dimension of V, which implies that u plus w itself is equal to V. And if it is equal to V, then I can choose the dimensions. Now, since, so automatically I can say that since B4 is LD, linearly dependent, because we know that if the vector space is dimension 4, then any vectors more than 4 will be always linearly dependent. So, I can from here, now I know that first 3 are linearly independent, that we already know, and the last 3 also linearly independent. So, I can maybe you can check from here that if I take the set, but if I take a set x minus 1, x square minus 1, x cube minus 1 and 1, so this is linearly independent. And if it is a linearly independent, it means I can take this as a basis of this one. And also we can check that, so I can check from here that the set x square minus 2x can be written as x square minus 1 minus 2 times x minus 1 minus 1, and x square So, this is x square minus 1, x minus 1, x cube minus 1, because from here you can say that x square and then it is minus 2x and minus 1 plus 2 minus 1. So, that will be 0, and x cube minus 3x can be written as x cube minus 1 minus 3 x minus 1 minus 2, because it is x cube and this will be minus 3 and this will be minus 2 and minus 1 minus 3 and plus 3, that will be 0. So, from here you can check that this and these vectors can be written as the linear combination of the vectors before that one. So, it means that these are the LD and we can remove this one. So, from here we can say that u plus w is equal to v and its dimension is the basis, another basis is this one. So, based on this one we can say like this one. Okay, so let me stop here. So, in the today's lecture we have discussed about that how we can define the subspaces u plus w, u intersection w, and how we can extend their basis to the dimension to the basis of the vector space V. So, thanks for watching, thanks very much.